But then I said, sort of empirically know one thing. Then I had a huge impact on what does it. If I do infrared spectroscopy, it's not a whole lot bigger. It's like something like 1,000, 2,000, 3,000 wave numbers. All the infrared peaks occur at about a few thousand wave numbers. And you have seen that. You have recorded these spectra. They're all like 4,400. So this would be like 4,400. And what the exact number is would be decided by what frequency or what transition it is you're looking at. But if you are a UV spectroscopist, then you not be something like 20, 30, 40,000 wave numbers. Quite naturally, this curve would have to be larger for the same temperature at the same molecule. So the UV spectroscopist, particularly ultraviolet spectroscopist, have to really contend with Doppler in a big way. Infrared, not so much. Rotation, I don't know never worries about the language of the Doppler. And if you're an NMR spectroscopist, you really don't have to worry about it at all. Because mu in that case is so small, and you will find that the line widths in such cases are quite sharp, and whatever width you have over there is due to some other properties and not really dominated by Doppler. So these two is something we need to keep in mind, and we must be able to work out quantitative problems based on these equations. I'll just tell you one more broadening mechanism, understand that qualitatively, and then we will not worry about the many other broadening mechanisms that we possibly have. But we will get the hang of it by then. I'm simply introducing you to all these because later on when you read many other topics, people will keep telling you the line is broadened because of some decay mechanism. But then you must say, yeah, I know that. Because we know that decay mechanisms will have an effect on the line width of the process. In this case, the decay is natural. Once it goes up there, it can't live there forever, and whether you like it or not, it will just come back after a certain period, given by an average value which we call as lifetime. And I told you that lifetime is an average concept. So it's 10 nanoseconds, it's an average value of 10 nanoseconds. While you have a chance to tamper with this width, how can you tamper with this width? In a given experiment, this you can't tamper with because the transition frequency is almost fixed. This you can't tamper with because the molecule you have chosen to work with is also fixed. But if you tamper with this temperature, you can lower the temperature, increase the temperature, and therefore the Doppler width is something that you can play with. You have some control over it. And people who do gas phase cold molecule spectroscopy have a huge advantage. All they do is take the molecule at high pressure, pass it through a small nozzle, and let it expand. And when it expands, it's called a cold molecular beam is produced. The molecule, when it expands, becomes essentially cold. And the temperature of that system will be like 1 Kelvin or 0.5 Kelvin or so on. But the nice thing is that 1 Kelvin is not a liquid or a solid. Because to form a liquid or a solid, what do you need? As you cool, molecules must start snatching each other, grabbing each other, and then form a solid or a liquid. But when I expand this, what am I doing? I'm pulling them. At the same time, I'm pushing them away from each other. So the guy cools, wants to solidify, looks around, there's nobody to catch on. And therefore, I have a non-equilibrium situation in which the molecule is very cold, wants to be a liquid, wants to be a solid, possible, but there are no molecules around to be a solid. I therefore have extremely cold molecules, but in the gas phase. And you can do experiments with these. And when the temperature becomes 1 Kelvin or 0.5 Kelvin, 0.1 Kelvin, what happens to this number? Oh, it's extremely small. And therefore, what happens to this number? This collapses. That's what I mean by saying that you can actually do experiments by tampering with temperature. It's not a thing you can do with natural width. And for those of you who believe in God, it's God. You can't touch it. So as here, the Doppler width is something that you can tamper with, simply by tampering with the temperature of the sample. If you want a bigger Doppler width for any reason, all you do is heat the sample. Temperature goes up. Therefore, you have a larger speed distribution, a wider speed distribution, and therefore a wider. Let's look at one more. And again, I got this problem. I take a molecule and put it up here. Molecule resides over there. And after its natural lifetime, whenever its fate is determined, it comes back. And that's the process which we call the natural lifetime, and that's the one that is equal by tau. Now, what I do is, I fill the system with a gas, so that While this molecule is up, before it has had a chance to come down, while it is still living its upstairs lifetime, another molecule comes and collides with it. So let's say this fellow has a lifetime of 100 nanoseconds, which of course would mean it could die in 2 nanoseconds, or it could die in 200 nanoseconds. The average is 100 nanoseconds. But let's say this particular molecule is destined to live there for 100 nanoseconds. Within that period of 100 nanoseconds, let's say the 50th nanosecond, a molecule comes and collides with it and picks up the energy, transfers the energy to itself. What do you think will happen to this molecule? This molecule will return to the ground state, not by emitting light, because the energy is not in the form of light that it has given off. This molecule has basically collided with this. This fellow has taken the energy, and this fellow returns to the ground state. This fellow has now picked up some energy, and it's therefore going to move faster. In other words, all you have done is you have caused an increase in the temperature of the planet. So the molecules are now moving faster. We call this as non-radiative decay. If this guy didn't collide, and this guy came down and gave me a photon, we call that as a radiative decay. Because it's given a photon and decayed itself. We call that as a radiative decay. But before it had a chance to radiatively decay, I had let it collide with another atom or molecule. Energy was transferred to that molecule. That molecule went screaming away because now it has excess energy, which it probably used in the form of kinetic energy. What happens to the initial molecule? It just comes back to the ground state, not having emitted light, but actually having given away that energy to another collider. But what if this keeps happening? What happens to the average lifetime of this molecule? Without the collision, it was there, its lifetime was 100 nanoseconds. But now if I increase the pressure in that system, by adding a gas, which keeps on colliding and taking away its energy at every possible collision, what happens to the overall lifetime of that state? It has to decrease. And when that decreases, instead of 100 nanoseconds, the lifetime would now be 50 nanoseconds, let's say. What will happen to the width of this line now? Get broader. The star has now become small and greater. In other words, I said that this is God given to get nothing with it. All I meant was that you can't increase it. But I can put gas in there, make it collide, decrease the lifetime, and when I decrease the lifetime, it has to increase, and therefore you will find that in high pressure situations where I have this gas at high pressure, a lot of collisions, the width increases. That's the reason if you ask people for a mercury lamp, and I have a mercury lamp for an experiment, the first thing they'll ask you is, you want a low pressure mercury lamp or a high pressure mercury lamp? Why? In a low pressure mercury lamp, what would you expect? Not many collisions. If you don't get many collisions, what will happen to the lifetime? Just natural lifetime. And let's say therefore that the mercury lamp now has emission that looks like each one of them being transitioned from different levels to different levels. So you see that the low pressure mercury lamp actually gives you a line spectrum. I take the same lamp, I pump in some argon in it or xenon in it, at pretty high pressure, a few atmospheres, seal it, and then I do the experiment all over again. The mercury will still absorb and emit. But what will happen to the lifetime of that mercury? It's decreased because I have thrown in a large amount of argon in there for collisions. Therefore, the lifetime decreases. What happens to the line width? It should increase. And now if you go back and look at the spectrum of this same lamp, high pressures, it might look something like this. In other words, if I want a source which is going to give me light over a wide range of wavelength, this is good. I get light at every wavelength. But if I want a source that needs to be used only for specific wavelengths, what would I do? I would use this one. The point is, we change the pressure of the gas inside the cell or inside your lamp, you can actually change the line width. How are you doing that? I'm doing that simply by increasing the number of collisions and therefore decreasing the average life of the molecule in the excited state. And this sort of a broadening, which is actually induced by collisions, you see quite naturally is called collisional broadening. So you have natural broadening, You have Doppler broadening, you have collisional broadening, and you have many other broadening mechanisms. Of course, what sort of collision is this? Elastic or inelastic? It's an inelastic collision because there's somebody changing mechanically, there's somebody changing potentially, and therefore this is an inelastic collision. It's very easy to understand why an inelastic collision actually broadens the line. Simply because in an inelastic collision, I actually decrease the lifetime of the excited state. And when I decrease the lifetime of the excited state, Professor Heisenberg shows me the line width will be large. And that's how it works. So you can ask me what happens if the collisions are elastic. It is still broadened, but the answer is a lot more complicated. You need to understand Fourier transformation to be able to figure out why that is. But rest assured, elastic or inelastic, it doesn't matter. The molecules collide. There will be a broadening of the spectral lines. So there are very many reasons. Three of them which we have seen: collisional, Doppler, and natural. There is something called pressure broadening. There is something called time of flight broadening. There is something called field-induced broadening, and so on. We wanted to get into all of these issues. If you become a spectroscopist, then of course you will have to learn all these things, because every time you do an experiment, these will be after you. The lines will be broadened by one of these mechanisms, and it is up to you to figure out what broadening mechanism is actually in operation in that particular experiment. It's extremely important to know that, because very often if you want to reduce a line width, you must know who is broadening in the first place. If you know who is broadening in the first place, if you know Doppler is the one that is broadening it, I lower temperature. If I know collision is the one that is broadening it, I lower the pressure, so on. Therefore, you must know who is broadening the line in the first place. So if you know that, then of course you can go back, remove that source of broadening, and get extremely sharp lines, if that is what you are looking for. The experiment that we do in our labs, yes, we need extremely sharp lines. And we have recognized that in all the experiments that we do, it's mostly Doppler and in some cases collisions that do it, and therefore we look at molecules at extremely low temperature, at 10 Kelvin, and under conditions in which molecules don't collide. And you can see that the lines will actually sharpen up, and they all become like one wave number or 1.5 wave numbers broad, as opposed to the 30, 40 wave numbers that few people have been seeing in the lab every time you record a spectrum. So what you should really do, if you have not done that yet, go back to the spectrum you have recorded, and then see what the width is. So the question now is, how do I define a width? Well, the width is great here, the width is great small here, and so on. How do I define it? Well, there is a certain convention that we use. We take the intensity of this line, let's say it's 10 units. We go to 5 units, half max, and then at that point we see what the width is. And then we say that is the width of the line. In other words, the width at half maximum is defined as the line width. So you could have given any definition. Width as 90%, width at 80%, whatever. Doesn't matter. But then we also speak a common language. And therefore we say that when I talk about the width of a spectral line, I'm actually talking about the width of the line at half maximum. Full width at half maximum. And that's the reason why you always see people giving you this term. So when you see this FWHM, it simply means it's full width, half max. Full width and half max. That's what it means. And that's how you define all these transitions. So when I say the line is broadened, or the line is sharpened and so on, when I say my line width is 1.5 wave numbers in my spectrum, and yours is probably 30 or 40 wave numbers, all I'm saying is go to half max, measure the width, and see what the width is. Most likely you will find it will be somewhere around 20, 30 or 40 wave numbers, depending on what compound it is you are looking at and what conditions it is you are looking at. However, if you go back and look at spectra the way we measure, it's like 1.5. You people did the hydrogen bonding experiments, right? So what did you observe over there? First, when the concentration was very large, meaning the solvent was in small quantities, you got a spectrum something like this. And then when you kept on diluting it, what happened? You started getting something sharp here. And then something like this. what are the two things you should have, or you have already noted there? First, this guy occurs at a higher wavelength. It's always at a higher wavelength. And what's the width of this compared to the width of this? It's much smaller than the width of this. Why? Over here, system is hydrogen bonded. They're all talking to each other, colliding with each other all the time. Whereas what happens in this case? This is a spectral feature of the monomer. There is no hydrogen bonding in that case. And therefore these set of molecules which have been diluted and completely devoid of any hydrogen bonding interaction are basically not undergoing any interaction. They're not talking to any of the molecules around. And that in fact collapses the line for the reasons we are talking about over here. So the first thing that you must have noticed there is that this line is actually much sharper than this. And second, this is occurring at a higher wavelength than all of these. And this actually is a telltale signature that this is non-hydrogen bonded and this is actually hydrogen bonded, which essentially was the whole essence of the experiment that you did the last few classes, where you're looking at hydrogen bonding. And what did you use? Ethanol, methanol? Ethanol in CCl4?
Yes.
No. So you got to use an inert solvent. So you just sort of break the hydrogen bonds. And if you make it very dilute, then of course the molecule tends to sort of disintegrate and tends to be in a more monomeric fashion. But if you increase the concentration of methanol, there's a great chance that it will start forming hydrogen bonds. And it forms hydrogen bonds. This is the white feature you get. So you have already been introduced to the fact that experiments can actually, depending on the conditions of your experiments, you can actually have white or small features, small width of features, sharp features or white features, depending on what your experimental conditions were. In fact, I think if you had gone to extremely high dilution, you probably would have even killed this off completely, and you would have had only this one. But of course, by that time, what happens is your concentration is so small that your spectrum now